Bismillahirrahmanirrahim. Dear students, we are talking about chapter number 5, grade 11, and this lecture number 43, and continuation of the intermolecular forces. In the last lecture, I told you about the dipole-dipole forces and London dispersion forces, and we explained how London forces are going to be operated. Now there are the applications of London dispersion forces. Applications of London dispersion forces. So factors affecting the London dispersion forces are atomic or molecular size. If the atomic size or molecular size is larger, these are the more effective. Polarizability is very high. Again, it is going to be more strong and effective. We will discuss. And number of atoms in a molecule, if are more, then again the London dispersion forces are going to be more effective or more strong. So one by one we are going to explain atomic or molecular size. Atomic or molecular size. Atomic or molecular size. So strength of the London dispersion forces depend upon the size of the electronic cloud of atom or molecule. So within the increase in size of atom or molecule, the dispersions becomes easy. The dispersions becomes easy and these forces become prominent. So this example is very important. If you see the inert gases in the periodic table, group number 8 from helium to radon, if you go down the group, the atomic size is going to be increased. You will find more electronic cloud. Shielding effect increases. Number of electronic shells are going to be increased. So due to this reason, the size of atom or molecule is going to be increased. The dispersions becomes easy and these forces become prominent. So if you see the table which is given in your book, boiling point of the noble gases, for helium, first element minus 268.6 degrees centigrade, the boiling point of the helium, which is near about the absolute zero, which is 273.15 degrees Celsius. And if you see neon, next element down, 245.9 minus, this is going to be increased. Argon, only minus 185.7, it is going to be again increased. Krypton minus 152, xenon minus 107.1, and radon is only minus 68.8 degrees Celsius. So dear students, if we go down the group, the atomic size of the inert gas is going to be increased. There are monoatomic molecules, they are not going to react. Their outermost shell is going to be complete by 2 electrons for helium and 8 electrons for the other elements. So due to the more electronic shells, size of the atoms going to be increased. So if the size of atoms are going to be increased, the dispersion forces are more prominent, and thermodynamic properties, just like you see, boiling point of all inert gases are going to be increased regularly as we go down the group. So this is the example of atomic or molecular size. Then polarizability. This is the factor which is going to affect the thermodynamic properties of the London dispersion forces of different elements and molecules. Polarizability of an atom to measure the date. Polarizability of an atom or molecule is a measure of the ease with which electron charge density is distorted.
If we are talking about the large atoms, previous I told you in the previous this atomic or molecular size,
large atoms have more electrons, I told you, and large electron cloud than small atoms, because number of shells are going to be more, so that's why large electronic cloud present in the large atoms, the size of atoms will be large. So in the large atoms, the outer electrons are more closely. In the large atoms, the outer electrons are more closely bound. They can shift towards another atom more readily than that of the tightly bound electrons in the small atoms. So in the large atoms, the number of electrons, number of the last shell is going to be the away distance is more from the nucleus. This is loosely bonded. This electron is loosely bonded, and if we can see the helium and also neon and argon, if you see the example for these atoms or molecules, even the size is going to be increased. Helium has only the two shells, only one shell. There is a atomic number is only 2. So K shell is complete. So it's nearest to nucleus. But if we see the radon and krypton, there are more electronic shells are there, and the outer electron is going to be more distance from the nucleus. So this is the loosely bonded. So large electron cloud than small atoms. The large atoms, the outer electrons are more loosely bound. They can shift towards another and more readily than that of tightly bonded atoms, means less smaller size atoms. This means that polarizability of the atoms increases as we go down the group, where atomic size is going to be increased. Electronic cloud is going to be increased. So that's why halogens, same example I'm going to molecules. These are the molecules here. Fluorine is a gas, smallest size. Chlorine is a gas, but bromine is a liquid, brown, reddish brown liquid. And iodine is a grayish or blackish solid. So this indicates that as you go down the group, the polarizability is going to be increased. These van der Waals forces are more prominent as the size of the molecule is going to be increased. So that's why thermodynamic properties, melting point, boiling point going to be increased, as I told you about the rare gases or inert gases. Because large molecules are easily polarizable, polarizability is going to be increased, more polarizable due to the more electronic cloud. The intermolecular forces between them are strong enough to form even liquids or solids. Bromine is a liquid and iodine is a solid. So this is a very important polarizability. Then number third is number of atoms in molecules. Number of atoms in molecules. Number of atoms in a molecule. So, dear students, if you see the organic compounds, alkanes, methane, with first hydrocarbon, carbon is only one, smaller size, ethane, propane, like this one. So as you are going to increase the number of carbon atoms, there are only 5 and there are here 6 and 8 and here are even more. So these number of atoms are gradually increases as we pass from one to another carbon atoms. Number of carbon atoms are going to be increased. So elongated molecules. These elongated molecules make contact with the neighboring molecules over a greater surface than do a smaller molecules. This is more elongated. This is a smaller molecule containing only one carbon atom. Elongated molecules make contact with the neighboring molecules over a greater surface than do the smaller molecules. So, greater number of the atoms present in a molecule has a greater polarizability. So, propane has more polarizability as compared methane. You can see the boiling point I have explained here. Boiling point of methane is a minus 161.5. Ethane is a minus 88.6. Propane is a minus 42.1 and decane is a plus 174.1. So as you go increasing the number of carbon atoms in alkane, the boiling point is going to be increased. First three members, methane, ethane, propane are the gases, butane is a liquid, pentane is a liquid, and also hexane, heptane, they are in the liquid form and the boiling point is going to be increased. So this is a very clear and great difference. Up to 4 butane only minus 0.5. Pentane 36.1, it is going to be increased liquid plus. Decane has a 174.1 plus. So there is a difference. Great difference if we increase the number of carbon atoms. That's why the very first line he said that elongated molecules make contact with the neighboring molecules over a greater surface than do the smaller molecules. So due to this reason, decane has a very high boiling point as compared the smaller number of the molecules which contain less number of the hydrogen atoms and carbon atoms. So dear students, these are the three factors I told you which are going to be effect on the thermodynamic properties. So these three are atomic or molecular size, polarizability, and number of atoms present in the molecule. Then there is another which you done in the lower class in grade 9. Hydrogen bonding. This is a special type of the intermolecular force, a special kind of intermolecular force which is created when high electronegative elements having lone pair of electrons. These high electronegative elements may be nitrogen, may be oxygen, may be fluorine. If they have a lone pair electrons bonded with hydrogen atom of another molecule. So this is a special kind of bonding which is called hydrogen bonding. Definitely is a type of dipole-dipole forces. Both forces are here. The difference of electronegativity between the bonded atoms is high, but there is a special name is given. We call hydrogen bonding. A hydrogen bond is an attractive force dipole-dipole force, intermolecular force, special kind of force. The lone pair of an electronegative atom, this is electronegative atom, nitrogen, oxygen and fluorine, lone pair, and the hydrogen atom that is bonded either nitrogen, oxygen and fluorine. So I'm going to give you example here, just like I'm talking about water. This is a permanent dipole, highly polar nature, difference of electronegativity is very high. This is a covalent bond, intramolecular force. There is a lone pair of the water. It is going to be affected with the hydrogen of other water molecule. This is the hydrogen of the water molecule. Also we call this is the dipole-dipole force, but according to definition, high electronegative element just like nitrogen, oxygen and fluorine. By the lone pair electron, this is a lone pair electron of the oxygen. It is going to be affected with the hydrogen of the other water molecule. Again, it is going to be formed also. Like this one. So this is the called hydrogen bonding. There are two lone pairs. It can form more bonds. We will explain here. In ammonia, there is a lone pair also. So it can form, nitrogen can form hydrogen bonding, fluorine can form hydrogen bonding. So this is a special kind of bond. The attraction between the lone pair of an electronegative atom and hydrogen atom that is bonded to either nitrogen, oxygen and fluorine. This limits of hydrogen bonded mainly to participation of nitrogen, oxygen and fluorine atoms. This is not a covalent bond, yes, friend. This is an intermolecular force which is very weak. Means if you are going to give energy heat at 100 degrees centigrade, this bond, hydrogen bond is going to be broken down and water is going to be evaporate or it can change it into gaseous state. We call splitted enthalpy of vaporization. So this is going to be vaporized, which is going to be changed into a steam, you can say, at 100 degrees centigrade. But this bond is very, very strong. Intramolecular force, covalent bond. So this hydrogen bond is much weaker than that of covalent bond. This is a very stronger one, and according to the studies, if you are going to give more than 2000 degrees centigrade, only I think 1% of this bond is going to be broken down. So highly strong bond, it is going to be only broken down when you pass electric current, when you put some acid or base in the water. Then electrolysis is taking place. Otherwise, no. So this is at 100 degrees centigrade. This bond is going to be broken down and water is changed into steam. So this is the hydrogen bond in the water. Hydrogen bond is weaker as compared to covalent bond, but stronger than dipole-dipole forces in the case of the hydrogen chloride. I told you in the previous lecture, in the case of also chloroform. So which is stronger than that of the hydrogen chloride and chloroform bond. So boiling point and heat of vaporization of water is higher than those of the this is the water and this is the hydrogen sulfide. This sulfide oxygen both belongs to same group. Atomic number 8, atomic number 16. If you go down the group, second element of the group number 6, sulfur. Both have lone pair electrons, but hydrogen bond is more prominent, much more stronger than that of hydrogen sulfide. Hydrogen sulfide is a gas, but water is a liquid, very, very weak intermolecular force, dipole-dipole force, because as we go down the group, the electronegativity of atom decreases. So sulfur has a very less electronegativity as compared to oxygen, which is the next highest electronegative element in the periodic table. That's why the bond between the hydrogen bond between the water molecules and hydrogen sulfide is a very great difference. So boiling point heat of vaporization of water is much more higher than that of hydrogen sulfide, because water molecules actually, if you see in the hydrogen fluoride, the difference of electronegativity in hydrogen fluoride is greater than that of water. The difference of electronegativity in the bond polarity between hydrogen and fluorine is much more than that of the water, but boiling point of water is higher than that of hydrogen fluoride. The reason is that because water forms more hydrogen bonds due to the two lone pair electrons. One water molecule forms more than one hydrogen bonds with other water molecules. Hydrogen fluoride only form one hydrogen bond with other molecule. Ammonia also can form one hydrogen bond with other ammonia molecule. So that's why hydrogen fluoride would form only one bond, and water form more than one bond, hydrogen bond with water molecules. Due to this reason, the boiling point of water is very high as compared to the hydrogen fluoride you can see down here. So the boiling point and heat of vaporization of water are higher than those of hydrogen sulfide, because water molecules attract each other through hydrogen bonding, where hydrogen sulfide molecules attract with the dipole-dipole interaction forces, because as we go down the group, the difference of electronegativity is going to be decreased. Sulfur is less electronegative than that of the oxygen. So this is the only about the hydrogen bonding. Now, what are the applications of hydrogen bonding? Applications, already we discussed here that water has a high boiling point, and ammonia is a gas S, and hydrogen sulfide is a less, hydrogen fluoride is less. So you can see here applications of hydrogen bonding: thermodynamic properties, melting point, boiling point, heat of vaporization, and other. So if you look the graph here in your book, horizontal there are periods, and vertical there is a boiling point of the different hydrides. Binary compounds of hydrogen are called hydrides. Binary compounds of hydrogen are called hydrides. So methane, carbon tetrachloride, silane hydride, ammonia gas, water, aluminum hydride, boron hydride, like this one. There are many. So binary compounds of hydrogen with other elements called hydrides. So if you look this graph, group number 4 element hydrides. Group number 4. So if you see the group number 4, methane, silane hydride, germanium hydride, and also tin hydride. So if you start from the methane, which has a very low boiling point, even less than minus 150 degrees Celsius, this is methane. But as you go down the group, the size of atom is going to be increased up to silicon. So it is going to be elevated, increase. Bond going to be more strong as you are going to move from top to bottom in the group number 4. Silicon hydride with more high boiling point, it is maybe minus 80 degrees centigrade like this one. It is going to be increased more germanium hydride and also tin hydride. Tin hydride is round about minus 45 or 46 like this degree centigrade. So size is going to be increased and involvement of d electrons and f electrons as we go down the group in the stronger bond is going to be operated between the germanium and tin with the hydrogen, because size is going to be increased and involvement of d and f electrons. But dear students, if you see, if you are going to see carbon, methane, then ammonia, then water, then hydrogen fluoride. Carbon group number 4, nitrogen group number 5, oxygen group number 6, fluorine group number 7. So if you see the graph here, group number 4 methane, first element of group number 4 methane, very weak force of attraction. Intermolecular forces, London dispersion forces are very weak indeed. So you will see the bottom boiling points are very low indeed. But as you go move to the other element of nitrogen, the same period, group number 5, so ammonia, it forms hydrogen bonding. So polarity is going to be increased. Polarity is going to be more. It can form a bonding with the hydrogen, with the lone pair electrons. So there the difference of the boiling point between the methane and ammonia. This oxygen with the hydrogen to make water, I already told you that water stop. If you see the graph, the boiling point of the water is the highest among all these. The reason because of the water molecules have 2 lone pair electrons, which can form more hydrogen bonding with the other water molecules. That's why its boiling point is very high, and it is going to be 100 degrees Celsius. This hydrogen fluoride, already I discussed you. This hydride hydrogen fluoride, even a strong bond is there due to the high difference of electronegativity between hydrogen and fluorine, but it can form only one bond. That's why its boiling point is less than that of the water. So dear students, as you are passing from one element to other element in the period, the boiling point is going to be increased, but here the difference between hydrogen fluoride and water already I told you. But if you see the groups, group number 5, ammonia, phosgene, arsenic hydride, antimony hydride. So if you see the from ammonia to phosphine, so it is going to decrease. Because nitrogen, smaller atom and more electronegativity than the phosphorus, so that's why it forms hydrogen bonding and phosphine normal dipole force. So due to this reason, the ammonia has a higher greater boiling point than that of phosphine. But as you go down the group, the metallic character increases, involvement of d and f electron in the atom in the bonding of hydrogen. So that's why you can see the green line is going to be increased, and antimony hydride is near about minus 10 or like this one. If you see for the group number 7, hydrogen fluoride is on top plus, it is greater than that of 0. About this is going to be about 25 or 30 degrees Celsius. It's a volatile liquid. So hydrogen fluoride is strong hydrogen bonding, but as you go down the group in the HCl, hydrogen chloride, the difference of electronegativity is less. That's why hydrogen chloride, the gas, must be in the negative. But if you are going to pass from the hydrogen chloride, hydrogen bromide and hydrogen iodide, you can see the difference of the boiling point is going to be increased. Already I told you polarity is going to be increased, and involvement of the d and f electrons and size is going to be increased. water stop because of it can form more than one hydrogen bonding with the water. So that's boiling point is 100 degrees Celsius. You can see orange line. So this water and hydrogen sulfide is a great difference. Hydrogen sulfide is a gas. Water is a very strong hydrogen bonding 100 degrees centigrade. It's a great decline of the boiling point as we pass from oxygen to sulfur. But if you go the hydrogen sulfide, hydrogen selenate, it's going to be slightly increases and it's going to be 0 degrees Celsius of the hydrogen tellurate. For the same reason I told you that polarizability will be increased as we go down the group. So please you have to read very carefully here. The boiling point of the hydrides of group 4 is going to be increased, and if you go the period from the carbon to hydrogen fluoride up to hydrogen fluoride, the water is going to be very high, but there is a difference between water and hydrogen fluoride. So please you have to go through this one, and already I told you this is same written in your book also. Now there is another application, solubility. What are the applications of hydrogen bonding when you are talking about solubility? You know that like solutes dissolve in like solvents. Polar ionic in polar, non-polar in non-polar. So dear students, if there are strong hydrogen bonding, they are definitely dissolved in the polar solvents. Just like water is a highly polar in nature, strong hydrogen bonding. Alcohol, organic compound, it is also highly polar. So they are highly miscible with each other due to the hydrogen bonding. So alcohol is very soluble in water. You can't make a saturated solution of alcohol with water. Very strong due to strong hydrogen bonding. Carboxylic acid, acetic acid, highly soluble in water. Glucose, sugar, they are soluble in water because they are polar. Then there is another one, cleansing action. We use detergents or soap to wash the clothes. Soap and detergents perform cleaning action. Their molecule contain, there are two poles. There are two parts of the detergents and also soaps. One is the polar part and another is the non-polar part. You know soap is prepared from the sodium hydroxide, which form polar part of the soap, and other is you are using fat oil or ghee. So this is the non-polar part. Same case for the detergents, they are organic compounds. They have sulfates, bisulfate and phosphates and other aromatic hydrocarbons are involved here. So their polar parts are water soluble due to the hydrogen bonding. Non-polar part dissolve grease and oil substances. So attraction between water and polar soap molecules carries all the grease droplets into the water. So this is the one thing only you done in the grade 10 maybe, that there is a difference between the soap and detergent. Detergents are called surfactants. They decrease the surface tension of water, they weak the hydrogen bonding in water, so equally they use in the hot water and soft water. But the soaps, they are not going to be used in the hot water for cleaning purpose, you know this one. Then there is another one, paint. Hydrogen bonding in paints and dyes, color. If the paint has more hydrogen bonding involved, this paint is more durable. It's not going to be, it is not coming from the wall in the long time. It's a good hydrogen bonding, so it is good action as well as in the all seasons, in the winter season, in the very warm season, in the rainy season also. so it should be very good. These forces are called adhesive forces. Paint and wall, different forces are called adhesive forces, and sand forces are called cohesive forces. Between paint and paint molecules, these are called cohesive forces. Between paint and wall molecules, these are called adhesive forces. So if the adhesive forces are very strong, it can be clipped with each other very strongly. Same case for the also in the honey sticky material. Honey is sticky material because of the glue, gums, they are sticky materials because of hydrogen bonding. There is also the property clothing. Same case I told you in the thread. If the hydrogen bonding is strong, then the fabrics which are made from the clothes, they must be a stronger one and lost lasting because of hydrogen bonding. Hydrogen bonding is very important in the fibers of clothing. They have great importance, thread making materials. This hydrogen bonding is responsible for their rigidity and tensile strength. Food materials. There are natural food materials, carbohydrates, they contain hydrogen bonding, glucose, fructose, sucrose, they contain hydroxyl group, they form hydrogen bonding responsible for this one. Biological molecules, they are very essential for our daily life. They have partly hydrogen bonding. Enzymes, protein molecules, catalyzes in the reaction, sustain the life, depend upon forming of the breaking hydrogen bonding. They are also hereditary information passed from one generation to other generation. DNA and RNA, they are joined by the hydrogen bonding. Dear students, these are the applications of hydrogen bonding. So in the next lecture, inshallah, we will discuss about the physical properties of liquids. Thank you very much.